This is BBC One. A very good morning to you again. Programmes for schools and colleges resume in 2 minutes with On the Rocks.
This Neapolitan ice cream, which is in fact a cliff on the right-hand corner of the Wash as you look north, is composed of layers. They're called beds. The thing about beds is that they have the characteristic of sedimentary rocks. Now, a sediment is anything that has been translated by a process like ice or wind or water to somewhere else and deposited. Now, in the British Isles, the most important contributor of those three processes is water. Most of our sedimentary rocks have been laid down by water in great bodies of still water, and they therefore form horizontal layers to begin with. The process, of course, involves a whole cycle. Erosion is producing material on the continents and sweeping it off into the sea, and it's being deposited. And this cycle is continuous. It goes on forever. Every time it rains, the drops of water dislodge tiny particles from the ground surface where they fall. Particles get broken from solid rock most effectively on high ground, where the weather is at its worst, and the bare rock of the mountains is exposed to all extremes. Frost and ice chip away at the hillside, and scree rolls downward, breaking up into smaller and smaller pieces. All these processes of weathering produce more sediment for the water to carry away. The carrying begins in high country, where streams move at speed, rushing and thrusting their way towards the lower pastures. In a glass-sided river, called a flume, you can take a fish's eye view of the stream and see that it carries small particles in suspension, but also tumbles quite big pebbles along the bottom. This wears and rounds their edges, as well as carrying them towards the sea. Big pebbles are left high and dry on the insides of the bends after floods, and the river appears to slow as it reaches lower gradients. But sand and smaller particles are still quite easily carried in the water. And of course, chemicals like calcium carbonate are actually dissolved in the water and carried that way. Finally, the river makes it to sea level. Its work is done, and it drops or deposits the rest of its sediment. The nice thing about beaches is that every day the tide prepares you a new clean environment, and there isn't any vegetation to get in the way. And in fact, you can return to your childhood and start playing with channels and canals, rather like Dad does after bedtime with the electric trains in the roof and things like that. In this case, we've got two pools and a channel between them, and I think if we let the water flow out of that one into here, we shall see what happens with sediments as they're deposited in a pool of still water, the ocean, for instance. The thing is that the beach is composed of a mixture of sand and mud and clay and silt particles, and what is happening is that the channel is carrying them all down to here and depositing all the coarse ones first. Can you see the gravel and the sand beginning to form a delta, and all the fine material in suspension is being carried on and is hanging about in this pool. And this is the way new rocks are formed, because the coarse material is dropped first. Sandstones and gravels and shingle are deposited close to the shore, so forever after we know they're shallow water deposits, and the very fine material is deposited way out in the ocean and sinks, and that's where our clays and then shales and so on are developed. A delta takes its name from its shape, a Greek letter D, like this satellite picture of the Nile, where the D is upside down. Flying rather lower, over the Mississippi Delta, you can see the balance that exists between the mud banks, that are the new land, and the sea. As the plants begin to colonize, they stabilize the mud, making its status as reclaimed land more certain. In Britain, we don't have simple deltas. We have wide estuaries, drowned by the great rise in sea level as the ice sheets melted. These estuaries contain our deltas, and therefore the sediments, but it's only noticed when the shipping lanes silt up and the dredgers move in. The finest material slides into deeper water off the continental shelf. The sediment-laden water moves very fast and spreads fine layers of material over the ocean bed. Very large amounts of our sedimentary rocks are marine sediments laid down in this way. They're called turbidites, after the turbidity currents that formed them, or a rather nice Victorian geologist's word, greywackies. They turn up far away from today's seas, for instance here in the Yorkshire Dales, and when the underside of the bed is exposed, you can see the flute marks made by the currents, as Maggie Calloway explains.
So what we're really looking at here is the bottom of one of these turbidite flows. This was produced by the turbidity current as it came down onto the ocean floor, and where it hit the floor, so it scoured out the soft bottom of the seabed. And these are the old scour marks, these lumps that we can see projecting from the underside of this bed. We can tell which way the current came from because the deepest scour would be the initial scour, and then the effect would taper out. And the deepest scour is the part of the projection which extends furthest towards us, and the effect tapers out. So on our bed here, the currents were in fact coming from right to left in that direction. They were coming from the east and flowing towards the west.
The sea itself is a pretty hefty erosive force. This Roman signal station now hangs precariously over the North Sea. And somebody got a nasty shock when they woke up and saw this out of the bedroom window. This is the Wash. Thousands of acres of land have been reclaimed here since Roman times. But the silt that makes these banks doesn't come from inland, washed down by rivers. This material is washed along the coastline by the sea itself. There are a number of problems about geological thinking, and one of them is deciding how on earth a loose sand like this, deposited in water, actually becomes a sandstone like that in the cliff. The thing you have to remember is that when this is deposited as a layer at the bottom of the sea, more layers are then deposited above it, until you've got thousands of feet of material, millions of tons of weight pressing down on this sand. It has two effects. It, first of all, compacts the whole material so that each sand grain is jiggled and moved about until it fits with the best fit to all the grains nearest to it. This reduces the spaces and leads to the second process, which is called cementation, in which the water that is in the original sand is squeezed out. The minerals that are dissolved in that water are then precipitated out and cement the grains together. Now, if we look at the cliff, then you can see that there are three layers. There is a layer of white chalk, and that was laid down in a biologically rich sea. Just below it there is the red rock, it's called, which was having washed into it the red iron oxides from a desert all around it. And that was used to cement that. And then below that is a brown sandstone, the Carstone, which has a brown iron oxide cementing it. The beds are separated by lines called bedding planes. Of course, there aren't just three beds here. There are a number of beds in each of the formations, and each of the near horizontal lines is a bedding plane. A bedding plane is always evident in sedimentary rocks, whatever happens later. So we tend to measure changes and tilts and folds by the position of the bedding plane when we see it. But the fact is that every bedding plane has at some point been the surface of the Earth. Out there in the sea now, another bedding plane is being formed as material deposits on that surface. I'm standing actually on a bedding plane that is the one between the chalk and the red rock. The boulder's actually tipped over as it's fallen off the cliff. So if you could turn me round, I would look like a Cretaceous bat hanging from under the chalk. Although sedimentary rocks usually form in horizontal beds, it isn't very often that you see them like this, in much the way that they were laid down. Almost always, great earth movements have heaved and uplifted the strata so that they are arched and bent. In this quarry, the rocks, which are Silurian sandstones, have been cut so that they show the bedding plane itself, bent into the single arch called an anticline. The beds which make this cliff are all but upended and then eroded by the sea into a challenge for any climber. He's abseiling down the bedding plane, down a surface that was once horizontal and underwater. This distortion, the folding and upending of rocks, is, with the faulting, or cracking and slipping of the beds, one of the signs that remain to tell us of the great movements our rocks have undergone. Not just once in geological history, but time and time again. Looking at the whole sedimentary process, and after all, sedimentary rocks make up most of our islands, these upheavals are vitally important. If all our mountains slowly eroded into the sea and no great lurch of the continent shoved new ones back up again, then there would be nothing to erode. The whole planet would be awash, and the only thing that might break the surface would be a featureless marsh. Down on the beach, where the sea cleans everything twice daily, you can see the attitudes of the sedimentary rocks most clearly. These beds of limestone and shale sloping towards the sea actually create for us a mini landscape. The difference in resistance between the limestone and the shale mean that we have a set of scarps and then gentler slopes. They run away from us into the distance. I'm standing on one of these scarps, and walking along the line of the scarp, I'm actually walking along the line that geologists call the strike. It's the line at right angles to the slope of the beds. In a minute now, I shall come to a point where I can turn off that line at right angles and turn up the slope, which geologists call the dip. And this we measure by its direction and also by its amount. It's sloping in degrees from the horizontal. The importance of these two terms, the strike and the dip, is that they tell us how the rock is behaving underground after we've lost sight of it. And both academic geologists who want to map what is where have to use these two measurements. And of course, the people who are interested in commercially exploiting the rock, as in coal, for instance, a coal seam is a bed, it has a dip and a strike, and by knowing that, you can predict how much you can get out and how difficult it will be to get it. Coal is made from the remains of extinct giant trees, but is still a sedimentary rock. So is this limestone, made from the bodies of millions of tiny animals. But quarries like this, where you can see the rocks without scrambling through a maze of bushes, are fairly rare and often private. So it's better to go back to the beach for the best views. British Rail have a train named after a geological period, the Devonian. But hanging out of its windows in South Devon, you can see not only that, but the new red sandstone as well. One of the things about redness is that it usually means iron, and it nearly always means heat geologically. And this colour is typical of desert rocks. In fact, this particular set of rocks are the things that accumulated at the edge of a desert basin, when mountains that were behind me, as it were being eroded by the wind and weathered particularly by temperature change day and night, so that everything was being split off. Pebbles explode in the desert because of the temperature change. It's that violent. And every now and then, perhaps the 365th day of the year, it does actually rain, torrentially. And then there is a great sludging of all the loose material down the slope. And these beds that you can see in the cliff are probably at the kind of angle they were at when they were deposited. They haven't been moved particularly violently. They sludged into position in this way. If you look closely at any one of these beds, it's like a porridge with bits of rock of different kinds all mixed up together. Rocks with recognizable bits of other rock in them are called conglomerates. And when they're all angular and broken, then they're called breccias. It's an Italian word meaning broken. And the thing you can find in the beds here are bits of broken rock from all the rocks that lie to the west of this particular place. And if you look at a geological map of that area, it is very complicated. There are limestones and volcanics and sandstones and slates and shales, and there are bits of all of them in these beds of what is really the base of the New Red Sandstone. It's the basement of Midland England. From here on the Channel coast, it goes up through Somerset, Gloucester, Worcester, Warwick, Stafford, divides round the Pennines, goes up the Lancashire lowland and up the Vale of York. Wind-blown sediments, like the sands of the desert, don't lie flat on the ground. The wind forms ripples, and also giant ripples that we call dunes. Exactly the same thing happens in a current of water, and when that water is carrying particles, they travel up the shallow upstream side of the ripple and drop down the steep side. This means that the front of the ripple is continually moving forward. Where there are strong tidal currents, the water also makes dunes or mega ripples, like these in Norfolk. You must have seen them in any sandy estuary. Obviously, if these processes are going on the surface of the beach as we see it now, they should have been going on all the time up till this level of the beach that the thing is building. And one of the ways of discovering that is, in fact, to take a sample downwards of the beach itself to see if the structures of the ripples, the dune-like ripples, are there down below. Now, you can't just shovel a spadeful out because you smear it and muck it up in doing that. So one of the simple ways of doing it is to push a tin without a bottom into the beach. All right, in. And then dig it out. There's only hand labour available for this, I'm afraid, but we've got to get the spade underneath the tin itself. Students from Glasgow University have taken samples like this on a far wider scale in the Solway Firth. Back in the lab, they cut away one side of the core and cover it with a thick resin. When this is peeled off, you get something like a plaster cast of everything that goes on for a foot below the surface. Many of the most obvious remains are of animals, whole animals like shellfish, and tracks and signs like these worm burrows. But there are also marks called cross-bedding, left by the ripples and dunes as the sediment has built up. These downward curves are also found in rocks, like this 800 million year old Torridonian sandstone in Scotland. It's the oldest sedimentary rock we have. And you can also see it in building stones, like the Portland stone in Waterloo Bridge. The cross-bedding in this block arches upwards, showing that the rock is set in the bridge the wrong way up. This one, on the other hand, lies the same way that it did in the quarry, exactly as it was laid down. Waterloo Bridge is also crammed full of fossils, hardly surprising as limestone is entirely made of animal remains. But in fact, fossils are only found in the sedimentary rocks. If you find a fossil, then you must be looking at sedimentary rock. Sometimes you find a whole animal, like this small sponge. But quite often you see instead what are called trace fossils, like the holes and burrows made by animals millions of years ago. These burrows were made by an ancestor of the shrimp. However hard the sedimentary rock, and however spectacular its scenery, don't be distracted. It's still possible to find exposures containing fossils and trace fossils. This is a particularly famous chunk of sedimentary rock, partly because it's so elderly We have a colour change which indicates two lots of beds, if you like, and you can see the lines of pale quartzite between red-stained quartzite. And the most interesting thing about this rock is that there are worm burrows down from the paler lines into the red beds, and they are filled in, of course, with the paler sand. Now, this is about 550 million years old, so these are very elderly worms. They're some of the oldest we know about. You can see the same thing today by letting a worm loose in a tank with layers of different coloured sand. All the animal traces that we see today are potential fossils. Burrows, footprints, worm casts, all could be the raw material for geologists a million years on. And some animals seem to be going out of their way to confuse the researchers of the future.